All right, guys, so here we go, 4.7. And we have this process that we're going to learn about. It has to do with solving quadratics when they don't factor, and when we learned how to work with problems that didn't factor but only had x squared in them, there was an approach we could use where we could isolate the x. The problem is that most quadratics both have an x squared and an x, which means the idea of isolating x by subtracting the 13 and peeling the layers off doesn't work. In fact, we really hit a roadblock here. There's not a good way to find the solutions to this equation. And so we wanted to find something else, and mathematicians worked long and hard trying to find algebraic methods for finding these exact answers that weren't obvious and that weren't easy to get to. And something interesting came out of it. And it has to do with first recognizing that there are certain perfect trinomials, perfect ones where when we factor, we get the exact same thing in both parentheses. Or in other words, that we could write it like this. There would be something squared. And so mathematicians really liked this version, and the reason we like this so much is because we would know that this first term would be x, and that there wouldn't be an x anywhere else in the problem. And because there's not an x anywhere else in the problem, okay, we then have the ability to solve this for x. So it's how do we turn an x squared and an x into a single x? So this is the mentality or the idea behind it. And the first thing that we notice, or the first thing that's going to make this simpler, is to remove the 13. That 13, it's not the right number for factoring an 8. If you think about it, 13 is only going to split as 13 and 1. We don't like that option. So we're going to rewrite this as x squared plus 8x. I'm going to leave a little bit of blank space and say that it equals negative 13. I've moved it over. At this point, I want to create this ideal setting where I'm going to get duplicate parentheses. Okay? And so the question is, what number would have to be right there in order to get a perfect split? The reason this concept is called completing the square is it actually has a lot to do with a square. If we take an area that we call x squared, that'd be x by x, and we take the area that is x by 8, right? So there's x and there's 8. What we're going to do is we're actually going to split this right in half, okay? Make it 4 by x. And this chunk we're going to cut off, and we're going to lay it right here. And what we find out is this is still x, and this is 4. So the question is, if I wanted to make a perfect square, I know this is x plus 4, and this is x plus 4 along the two sides. The question is, what's in this corner that I would have to add into the problem to create this perfect square? Well, if I recognize that this is 4 this way, and this is 4 this way, that 4 by 4 would give me 16. 16 is this perfect number that would allow me to split this just right. So if I added 16 into this side of the equation, I would also have to do it over here. And by adding that 16 to both sides, the factoring on the left becomes super easy. So then I would have x and x. The 16, to split it so that it adds up to 8, would be 4 and 4. That's extremely important that they end up being the same. We have to have them match. And the 16 is positive, which means my signs are going to match. And to get a positive 8 in this case, I'll have plus and plus, which allows me to write x plus 4 as a quantity squared equals 3. If we look at the problem now, we notice that the x only occurs once in the problem. Now, depending on the problem you're going to work on today, this might be a stopping point. It might be a point we go forward from here. There's a couple of different things that you'll do in the assignment. But if I wanted to solve this original problem, I would now start peeling layers by taking a square root to get x plus 4 equals plus or minus root 3. And then I would just have to move the 4 over and get x equals negative 4 plus or minus root 3. Now if I wanted to go and graph this quadratic, negative 4 is going to be right in the middle, and to the right 1.73 and to the left 1.73, I would have my parabola looking something like this. Don't judge me on my parabola, but it would go through those 2 points, negative 4 plus root 3 and negative 4 minus root 3. We found the places it crosses, and we did it without the graph, which, by the way, wouldn't have been very helpful because it's an irrational number, and we did it without having to do some guess and check. We were able to find that answer directly. This is completing the square. Everything else we do is going to be about manipulating complete the square into producing specific results. For instance, let's imagine that instead of saying equals 0, this had started with equals y. Okay, so then right here, okay, right here, this stage, we would have x plus 4 quantity squared equals 3 plus y. Instead of being plus 0, it would have been plus y. Then if I get the 3 moved to the other side, I would have y equals x plus 4 quantity squared minus 3. The reason this version is so helpful is it tells me that the vertex is at negative 4 comma negative 3. If you remember finding the vertex in a parabola from the vertex form. So we can use completing the square to go from standard form to vertex form, and that's actually going to be part of what you do in your quarter project. So this idea of completing the square allows us to solve problems and to rewrite things in formats that might be better for us. Hopefully that's enough to kind of get you the basic idea, and then you'll see some help in the homework video as well. Good luck.